Hello everyone, this is Dr. Armand bringing you another exciting lecture on general chemistry. Today we'll be talking about molecular orbitals. So how do electrons behave in molecules? We're looking at very simple ones. So we're looking at molecules that are homonuclear diatomic, so two of the same atoms. We'll be looking at molecular orbital configuration and how to do orbital diagrams of molecular orbitals as well. Kind of a bittersweet moment. This lecture is the last lecture of the series of lectures that we've been having over the course of the last few months. So in some regards, this is like the season finale of my lecture series. So I hope you've enjoyed it. And as always, hit the like button if you like the videos. So sit back, relax, and enjoy the show. All right. So this is the third installment, I believe, in chapters 9 through 11, or maybe the fifth installment. I'm not sure, I lost count. But mainly today's goal is to focus on what are molecular orbitals, how do we describe electrons in molecules, how do we write molecular orbital configuration, and draw the orbital diagrams of molecular orbitals, and also determine if a molecule is paramagnetic, meaning it has lone electrons, or diamagnetic. So with molecular orbitals, there are two types of molecular orbitals. Just like you have types of atomic orbitals, we have types of molecular orbitals. And there are two main categories of molecular orbitals. And these are bonding molecular orbitals and antibonding molecular orbitals. Now, bonding molecular orbitals, there's a region of electron density between the two atoms. So this red circle here, this is the region of electron density between the two atoms. It's also the sum of wave functions added together. Also note that these are lower in energy than atomic orbitals due to the decreased nuclear repulsion and the increase in nuclear electron attraction. So these are what bonding orbitals are. Antibonding molecular orbitals have a region of zero electron density between the two atoms, which I've circled here. And this is a result of subtracting the two wave functions, and this resulting orbital is actually higher in energy than the corresponding atomic orbitals. So that means there's electron density outside the internuclear region, which is this region. This is the internuclear region. There's a node there. These are less stable than individual atoms. That's why they're higher in energy, and they have more nuclear repulsion because they don't have that electron density between them. So these are the two types of molecular orbitals. So how do we put electrons in molecular orbitals? Well, we use the off-ball principle, so we start with the lowest energy level first and work our way up. We also apply Hund's rule. Each degenerate orbital gets one electron before you pair them up. And we also apply Pauli's exclusion principle, which means that no two electrons can have the same set of quantum numbers. So we have one pointing up, one pointing down. Now, one thing we're able to determine from molecular orbitals is the bond order, which is half of the number of bonding electrons minus the number of antibonding electrons. And if the bond order is greater than 0, it means it's more stable than the separate atoms, and it will form. If the bond 0 is equal to 0, it means the molecule is stable. Its molecule is not stable, it's more stable as separate atoms and will not form. So the higher the bond order, the stronger the bond. So here on the right-hand side, we have the molecular orbitals for H2. So again, each H has a 1s atomic orbital. When we add those two 1s atomic orbitals together, we get a sigma 1s molecular orbital. So when we add the two atomic orbitals together, it produces a molecular orbital that's lower in energy called a sigma 1s orbital. Now when we subtract those two atomic wave functions, we get an antibonding orbital, which is higher in energy. And so for H2, which has one 1s electron, we fill the lowest energy level first, which means there are 2 electrons in the sigma 1s orbital and 0 electrons in the sigma star 1s orbital. So the bond order is equal to 1/2 times 2 minus 0 gives us 1. So this tells us there's a single bond between the 2 hydrogen atoms. So that's hydrogen, very simple molecule. So now let's look at helium. Helium has 2 1s electrons, but we're looking at helium 2 plus, so we remove one of the electrons from it. So again, helium, each one has 1 2s electron, but since it's helium plus, we remove one of the electrons from it. And so now when we fill the orbitals, we start with the lowest energy level first, so we add 1 from each one. We fill this completely filled. That's 2, but we have to put 1 more, and it goes in the antibonding orbital. Whenever you put electrons in antibonding orbitals, they become very unstable. So the bond order is 1/2 2 minus 1, which is 1/2. So it's something almost like a single bond. Now if we look at helium 2, so diatomic helium, we see that now we have a completely filled sigma 1s and sigma star 1s orbital. So whenever you have completely filled bonding and antibonding orbitals, the bond order is going to be 0. So again, whenever you have completely filled bonding and antibonding orbitals, the bond order is going to equal 0. So this tells you that helium 2, diatomic helium, cannot exist. And what we do is we write the molecular orbital configuration just like we would atomic orbital configuration. So this is for He2 plus, it's sigma 1s2, sigma star 1s. For He2, it's sigma 1s2, sigma star 1s2. You do it just like you would atomic orbital configuration, but you do it with molecular orbital. So what they're asking is, would He2 2 plus exist or H2 2 minus? Now H2 2 minus for H2 2 minus, this would have 4 electrons, which would relate to having a completely filled bonding and antibonding orbital. So since they're completely filled, this is going to have a bond order equal to 0. So if I just go to the last slide, if we have H2 2 minus, we're going to add 2 electrons, extra electrons to the 1s orbital. So now we have 1, 2. This is H2 2 minus. So that means these electrons go in the antibonding orbital. And notice here that for H2 2 minus, we have the same number of bonding and antibonding. They're completely filled. So the bond order for H2 2 minus is 0. Now for He2 2 plus, For He2 2+, we got to remove 2 electrons from it. So it's just going to have one 1s electron for each helium. So this one goes away. So He2 2+ only has 2 electrons in the sigma 1s orbital. So therefore, the bond order equals 1/2 times 2 minus 0, which equals 1. So this would have something like a single bond. So this would exist. So you don't have to memorize the chart. You just have to know that, okay, for helium, we have 2 1s electrons in each, but since it's helium 2+, we have to remove 2 electrons, so we get only 2 electrons, 1 in each 1s orbital, so then we get sigma 1s 2. Now, this is good for the first row, so hydrogen and helium, we know how they behave as diatomic molecules. But for lithium and beryllium, we would go to the bonding occurs in the sigma 2s orbital. Because each lithium has one 2s electron, so if you have 2 of them, it's going to form sigma 2s is going to be completely filled. But for beryllium, you see that we have a completely filled sigma 2s and sigma star 2s. Whenever you have completely filled bonding and antibonding orbitals, you're going to have, it's going to be highly unstable. The molecule is not going to exist. So the molecular orbital configuration is sigma 2s2, sigma 2s2, sigma star 2s2 for beryllium 2. Oops. And so the bond order would equal 1/2 2 minus 0, which would be 1. So lithium diatomic molecule would have a single bond. Whereas beryllium, the bond order would equal 1/2 2 minus 2 equals 0, so therefore molecule would not exist. And so when you have a sigma bond like a sigma bond is called a single bond. So if we have, for example, 2 lithiums, a sigma bond is a lobe of electron density between 2 atoms like this. That is a sigma bond. It's a lobe of electron density between 2 atoms. Every single bond is a single sigma bond. Remember that. All right. So what does a sigma bond look like? Well, we just talked about it. But with the hydrogen atom, the two atomic orbitals, we can add them together to get a bonding molecular orbital. So this is what a sigma bond looks like. It's this region of electron density between two atoms. It's a lobe. That's a sigma bond. And so every sigma bond, a single bond, is a sigma bond. And then we have antibonding, where you see the node or the region of zero electron density between the two atoms. That's from subtracting the two atomic wave functions. So again, sigma molecular orbitals or sigma bonds are cylindrically symmetrical around an axis between the two nuclei. So it's this lobe or cylinder of electron density between two atoms. Every single bond has a sigma bond. Every bond, in fact, whether it's single, double, or triple, has a sigma bond. So again, every bond, regardless if it's single, double, or triple, has a sigma bond. So now that's with the S block diatomic molecules. What about the P block, second row P block diatomic molecules? And so with these, we have to introduce p orbitals, because everything from boron to neon have electrons that fill the p orbital. So we're going to be adding and subtracting atomic p orbitals to produce molecular orbitals. And so there's two ways we can add these. We can add these end to end, where we get a pair of sigma molecular orbitals, or we can add them side to side, which gives us a pair of pi molecular orbitals. So what you need to remember is that the molecular orbitals from the 2s orbitals are lower in energy than the 2p orbitals. So we don't see them right now. That's below the molecular orbitals for 2p. And so sigma 2p molecular orbitals are usually lower than pi 2p molecular orbitals. So again, sigma 2p is when you have an end-to-end overlap of molecular orbitals. So this right here is an end-to-end overlap of atomic orbitals to produce a sigma 2p molecular orbital. And of course, its corresponding antibonding orbital. Now, when you do side-to-side addition, you get what's called pi 2p bonding molecular orbitals. So they contain 4 electrons. And then you get the corresponding antibonding pi molecular orbitals. So typically, the sigma 2p molecular orbitals are lower than the pi 2p, and the sigma star 2p molecular orbitals are greater than the pi 2p. So this is the order of increasing energy. So as you see on the next slide, as if you were to rank them, that's how they would look. So now there are 2 categories on this P block for the period 2. Those that do not have S and P orbital mixing, so they're the heavier second row P block elements, such as oxygen, fluorine, and neon molecules. Here the S and P atomic orbitals are so different that no interaction occurs. And there's a big difference, there's a big energy gap between the 2p orbitals that raises the atomic orbitals. So there's a big energy gap between the sigma 2s and sigma 2p atomic orbitals. But with the lighter 2p blocks, such as molecules of boron, carbon, and nitrogen, there is some mixing that occurs between the s and p atomic orbitals. So what happens is this lowers the sigma 2s and sigma star 2s orbitals and raises the energy of sigma 2p and sigma star 2p. And we'll show you how that affects in just a second. And so if we look at the molecular orbitals without S and P mixing, you see that the sigma 2p and then it's pi 2p molecular orbitals, then pi star, and then sigma star. But with S and P mixing, you see that now there's a greater energy gap between the sigma star 2s and the 2p orbitals, and that the sigma 2p and pi 2p atomic orbitals have switched positions. So if you're doing molecular orbitals for the lighter 2p molecules, you use the one with mixing. If you're using the molecular orbitals for the heavier 2p orbital molecules, you use the one without mixing. So this is the difference between the two, and when do you use one versus the other. So here we want to route the molecular orbitals for the bond orders of C2 minus, C2, and C2 plus, and determine the bond order. So first we're going to start with C2. So let's put C2 has two 2s electrons. And again, this is energy. And since it's carbon, we do the one with S and P mixing. And so there's a completely filled sigma and sigma star 2s. No surprise there. Now for 2p, it has two 2p electrons. So again, you do Hund's rule, you put one in each. Notice that pi has two degenerate orbitals, and then we pair them up. And so the bond order one half, there are 6 bonding electrons and 2 anti-bonding. So that would be bond order of 2. So there would be a double bond in this molecule of C2. Now let's look at C2 2 minus, or C2 minus. And what we're going to do is we're going to add an extra electron in one of the atomic orbitals. You just got to add one of them. I'm just going to add one for C2 2 minus there. So that means they're going to have one in the sigma 2p atomic orbital. So the bond order here is one half 7 minus 2, no, 6, yeah, 7 minus 2, which is a 2.5. So it means it's somewhere between a double bond and triple bond. Next we have C2 2 plus. So first I'm going to remove the extra electron I added so we get back to C2. Now for C2 plus, we got to remove one electron. It doesn't matter which electron you remove, but remove one. And we got to remove, one from pi 2p, because there's only 3 there. So the bond order, one half, we have 5 minus 2, 1.5. So this be somewhere between a single and double bond. So also you can notice that C2 2 plus and C2 minus are going to be paramagnetic because they have a lone electron. Whereas C2 is diamagnetic, it has only paired electron. Now, let's look at one that does not involve S and P mixing. So here we want to know what's the molecular orbitals and bond orders for F2 minus, F2 minus, and F2, F2 plus 2. So again, we're going to start with F2, and then we'll go from there. So F2, let's put in the electrons. Pretty much for the 2p diatomic molecular orbitals, the 2s is always going to be completely filled. Now, each fluorine has 5 2p electrons. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the bond order for F2 is we have 2, 4, 6, 8. Let's see, is that right? 6, 8. 8 bonding electrons. And 2, 6 antibonding. So that gives us a bond order of 1. So F2 has a single bond. Also, it's going to be diamagnetic because it has no lone electrons. They're all filled. Now let's go to F2 minus. So what we're going to do is we're going to add 1 electron to the atomic orbital of one of the fluorine's atomic orbitals. So not that, undo. So we're going to put it here. So since we added an electron, we got to put it, and it goes up here. So the bond order of F2 minus is equal to 1/2 8 minus 7, which is 0.5. So it's like half a bond. It's not very stable. And this is paramagnetic now because it has a lone electron. Now let's go to F2 2 minus. So we're going to add another electron to the one of the atomic orbitals. So I'll add it here. And that electron goes up here. So now the bond order becomes and so this one does not exist because it has a bond order of 0. So now let me erase all the additional electrons we added. Oh, snookies. All right, now let's look at F2 2 plus. So to get F2 2 plus, we have to remove 2 electrons from the atomic orbital. So I'm going to remove 1 from here and 1 from here. Let me undo that. Yeah. So we removed 2 electrons, 1 from one atomic orbital, 1 from the other. So now we have a total of 8. So we got to remove 2 electrons from here. Now, according to Hund's rule, each one gets 1 before we pair them up. So the bond order would equal 1/2 8 minus 4, which equals 2. So this would have a double bond, something like a double bond, and be paramagnetic because now it has lone electrons. So again, the main thing is to pick the right orbital diagram. If it's fluorine, oxygen, or neon, you pick this one. If it's carbon, boron, or nitrogen, you pick the one on the previous slide with S and P mixing. Now, one more example. We have the following molecules are diatomic. Which ones are diamagnetic? Meaning they have no lone electrons. So F2 minus, we notice, did have a lone electron. So this one, we did notice from previous slide, has a lone electron. We just got to do these here. So let's look at oxygen first. O2. Oxygen, we got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So the 2s, of course, is completely filled. And then we have 8, so it'd be 1, 2, 3, 4, 5, 6, 7, 8. So O2 is paramagnetic, so it will not be O2, it will not be F2 minus. F2 plus means we remove 2 electrons, so let's do that. Let me do it the right way. One too many. Then we need to remove 2 electrons from the molecular orbitals. You can see O22 plus is diamagnetic because it has no lone electrons. Now let's look at neon. So what's unique about neon? Neon has a completely filled 2p orbital. But since it's neon plus, we're going to remove 1 electron. So now we get that. So neon 2 plus is paramagnetic. So only O2 plus 2 is diamagnetic. So you're looking for the ones without lone electrons. So that concludes the final bit of lecture over the last parts of chapters 11 dealing with hybridization molecular orbitals. So again, the main thing here we want to discuss is that molecular orbitals are a way to describe how electrons behave in molecules. You have bonding molecular orbitals and antibonding. So bonding a result of adding wave functions, antibonding a result of subtracting wave functions. Now we did mention sigma bond is equal to 1 single bond, or a single bond, I should say, contains 1 sigma bond. Double and triple bonds contain 1 sigma bond. So everything contains a sigma bond, which is that cylindrical lobe of electron density between 2 atoms. Now, double bonds also contain 1 pi bond. So that's a total of 1 sigma and 1 pi. Each double bond contains 1 sigma, 1 pi bond. A triple bond also contains 2 pi bonds. So therefore, each single bond, or each triple bond, excuse me, has 1 sigma and 2 pi bonds. Then we notice that for homonuclear diatomic molecules, for the 2s molecules is not that bad, lithium and beryllium, but for the 2p, we notice that to get, when we have p orbitals, we have end-to-end overlap, which gives us sigma 2p, sigma star 2p molecular orbitals, and side-to-side overlap that gives us pi 2p and pi star 2p molecular orbitals. And the pi's can hold a total of 4 electrons in them. And then for those lighter 2p molecules, such as boron containing boron, carbon, or nitrogen, they do the molecular orbital diagram with the mixing. And the oxygen, fluorine, and neon are the orbital diagram without the mixing. And so that concludes this lecture series over general chemistry. I hope you enjoyed the lecture series. You've learned from it. This is the season finale, so you won't be seeing me again unless you take Gen Chem 2, and we're still doing online courses. So good luck on your exam, and I hope you've enjoyed it. And make sure if you liked it or learned something new to click like on the video. And on that note, Dr. Armand signing off. Have a good break.